I don't know if you heard me or.
Thank you, Ashraf.
And
no, I can understand that they are preliminary.
Yeah.
For me, the really concern was the frequency of the model and so on.
We just had a discussion 5 minutes before this presentation about that, because I could see clearly the difference, and it seems that there is some difference in the data. So we need to be clear which ones to use and which ones are more accurate. So
sure.
Yeah. So we'll discuss that later.
Okay, thank you, Dr. Ashraf. Thank you, Piero. Thank you, Mohannad. I think now we have another 3 minutes. Do you hear me? Can you hear my voice?
Yes, I can hear you, yes.
Okay, so we have 3 minutes and please, Mohannad, stop sharing your screen. Then Dr. Emad is with us here from Fayoum University, actually, and he's working in our group here. He made modeling of Cairo Citadel, and he's planning to put Viba also in it, in his model. Emad, are you with us now?
Yes, doctor.
Okay, great. You can share your screen now. And I believe you can start within 2 minutes your talk. You have 2 minutes still. Emad, are you able to share your screen?
I am already sharing the screen.
Okay. Can you see the screen? See, the screen is not shared in front of me, but I will be waiting. It's not a problem. Emad, you have to share your screen. It's not shared yet. Okay, it is okay now. It is okay now. Okay, Emad. I believe you can start now. It is actually on time.
Yes, doctor. At the beginning, I would like to thank Dr. Yusuf Rashid for giving me the opportunity to participate in this workshop among those great professors. And thanks should be extended to Dr. Ahmed Fadi and all COFB team for supporting me. I will talk about in this presentation three-dimensional modeling of Cairo Citadel. Presentation contents, introduction is the first text section, Cairo Citadel scanning, Citadel and soil properties, numerical modeling of Cairo Citadel analysis, static and dynamic, Viba effect, summaries and conclusion. Aim of the presentation, illustrating the steps of creating a three-dimensional model of Cairo Citadel, demonstrating the static and dynamic response of Citadel, illustrating the effect of using vibrating barriers on the dynamic response of the Citadel. Why 3D numerical modeling of Cairo Citadel is important? Because Cairo Citadel is one of the most important monuments in Egypt. The complexity of the Citadel geometry, difficulty of performing dynamic analysis for the Citadel, especially in the existence of Cairo Citadel scanning. coordinates of 30 degree north and 31.15 degree east, and this figure represents the snapshot from Google Earth. Cairo citadel parts. Citadel consists of two parts.
Emad, in front of me the slide is frozen. Can you change the slide, or this is something from the internet? Okay, now. We haven't seen the previous slides, so can you repeat, please?
This slide?
We haven't seen except the first slide, the title slide. You can start from the second slide or something like that, because we haven't seen it.
This is the second slide.
Okay, okay. You can start now. Okay.
Presentation contents. Okay. We have 7 sections. The first section is the introduction. Second section is the Cairo citadel scanning. The third section is the citadel and soil properties. Fourth section is representing numerical modeling of Cairo citadel. Number 5, Cairo citadel analysis, static and dynamic. Number 6, VIBA effect, VIBA modeling and its effect. Finally, summaries and conclusion. The aim of the presentation, illustrating the steps of creating 3-dimensional model of Cairo citadel, demonstrating the static and dynamic response of the citadel, illustrating the effect of using vibrating barriers on the dynamic response of the citadel. Why 3D numerical modeling of Cairo citadel is important? Because of Cairo citadel is one of the most important monuments in Egypt. Complexity of the citadel geometry, difficulty of performing dynamic analysis for the citadel, especially in the existence of VIBA. Cairo citadel scanning, section number 2. Cairo citadel location. At the coast of 30 north and 7.15 east. This figure represents a snapshot from Google Earth, Cairo citadel. Citadel is considered part the mosque and part. Cairo, this represents a
Emad, please change the slide. Emad, the slides are frozen. Please change the slides. Wait a second.
You see the slide now? The file is very large. Citadel and soil properties. Mechanical properties of the citadel. Samples from the stones inside the site were tested in the lab for determining the mechanical properties of the materials used in building of the citadel. The material of the citadel structure was limestone, which is density is 2,700 kilogram per cubic meter. Elastic modulus is 47 gigapascal. Poisson ratio is 0.2. Mechanical properties of the soil. A borehole with a depth of 10 meters were dug to determine the properties of the soil in citadel area. This is the soil profile. The first meter was backfill, and the remaining 9 meters was limestone, which is the same material used in the citadel structure. Has the same mechanical properties of the material used in the citadel structure. Numerical modeling of Cairo Citadel using abacus. The numerical modeling of Cairo Citadel was done using abacus software. Here, after drawing the AutoCAD file, it was saved as DXF file and imported to the abacus. This figure show how to import the DXF file to abacus using import sketch not model and select DXF file. Citadel element types. Domes and wall elements are shell elements of type S4R, which is 4-node linear thin or thick shell elements. The columns are solid elements of type C3D8R, which is 8-node linear brick element. This figure shows that we have to convert the shell elements of the columns to be solid elements as shown in the figure, because when we importing the DXF file from CAD to the abacus software, all parts or and elements of the citadel become shell elements. So the solid element should be converted from the shell element as shown. Mesh technique of the citadel mosque. We have two techniques of mesh technique. For the solid columns, we used the structure technique because it is regular, and for domes and other parts of the citadel, we used the free technique because of the complexity of the meshing. This figure represents the overall citadel mesh. Modeling of the soil. Soil dimensions, element types, and mesh technique. Soil dimensions was 215 by 215 by 40 meters. This figure, in this figure, the green blocks are solid element of type C3D8R, which is 8, which is 8-node linear brick element, and the yellow blocks are semi-infinite of type CIN3D8. We used here semi-infinite element to avoid the reflection of dynamic waves. This figure represents the overall soil mesh. It is clear from this figure that the size of element in the middle is different from the element at each. Assembling overall mesh handle the soil constraint which tie rotational degree between the soil. This figure represents a set overall mesh for the citadel and the soil. Here we record in the and this figure to insert the quick record the abacus magnitude. We estimate the displacement magnitude for 3 points in the top top. For the dynamic response, this is a short video illustrating the dynamic response for Aqaba with another short video for the response of the citadel to
fine-tune. But really, I mean, I'm really well done. We will work in the following for tuning. Will be really a great pleasure.
Thank you, Piero, for this. And I'm experiencing here some connection problem, to be honest, and we are the host. So we are trying to sort out this problem. But definitely, Piero, we will need your help in designing the bypass because we have some sort of many ruts, and I believe it will need some sort of special arrangement of this bypass in order to reduce the response.
Yeah, no, you
So,
know, one of the key difference indeed
okay,
is.
continue.
Can you hear me? I was saying
I can hear you.
One of the key issues indeed is to calibrate to the right frequencies, or to have an internal unit with a broadband capacity, so playing also with the damping in order to absorb specific frequencies, a range of frequencies. As I said, it is not trivial. This is a very complicated case. But I mean, that is will be the interesting part of the research. Can be done. I mean, these results that already you showed 12% of reduction can be definitely improved. I have no doubt from this point of view. So we'll see what we can do.
Definitely, but at least, Yes, at least at the moment we have the 3D model, the solid 3D model, which I believe it is at least more than 50 to 70% of the problem, because it was very difficult to model such a complicated structure. And I believe Dr. Emad is time.
Oh, yeah, I see that. This is indeed why I congratulate for the massive work. I see. Also very well presented. Thank you to the speaker to present very well this work.
Thank you, Piero. Thank you, Dr. Emad. Anybody want to ask any question? Just unmute yourself and continue directly.
Maybe a quick comment, Dr. Youssef. This is again. I think the page of Piero is very clear that the VIBA is very efficient, but it has to be properly designed. You cannot just put it from the previous 2 or 3 presentation. It has to be optimized and designed and tuned to the right frequency so that it has an effect. I understand you have like a 12% reduction. It could go easily up to say 40%, I believe, Piero, if I'm not mistaken. So anyway, that's just a quick comment. But my question to Dr. Emad, your model is very complicated because you have many sub-elements there within the citadel and stuff, plus the soil. Because it's an issue for us as well. Is it days or hours, or like, can you give us, because this is a very numerically expensive problem. Particularly if you go into the nonlinear you do, it's going to be even take more time.
I solved the problem as a linear. It take about 1 hour.
Just 1 hour?
1 hour.
Okay. And I think in some, I don't know, in some cases it could take days. At least in our case, we observe it could be the nonlinearity that we're introducing.
I will include the nonlinearity model.
Yeah. All right, thank you.
For this, and I believe we have speaker Professor Alex Chang. So we will have another cup of coffee or tea or something like that in the coming 30 minutes, and we'll be back after 30 minutes from now. Less than 30 minutes, something like 25 minutes. Okay? Let's see the headshot.